Hello and welcome to Solved, where we help you solve problems. In this video, we will be discussing the solution to a natural convection system coupled with unsteady state conduction. So let's begin with the problem. Rubber balls are molded into spheres and cured at 360 Kelvin. Following this operation, they are allowed to cool in room air. What will be the elapsed time for the surface temperature of a solid rubber ball to reach 320 Kelvin when the surrounding air temperature is 295 Kelvin? Consider balls with diameters of 7.5 centimeters. Properties of rubber that may be used are K is equal to 0.24 watts per meter per Kelvin, density is 1,120 kilograms per cubic meter, and heat capacity is equal to 1,020 joules per kilogram per Kelvin. As a preface before we solve this problem, this involves natural convection and the unsteady state's conduction of heat through the rubber ball. Okay, we will start with the natural convection part. For the first half of our solution, we will be using our concepts of natural convection in order to get an estimate of the value of the heat transfer coefficient and then later use that in unsteady states conduction. Okay, here we have the given to the problem. Our rubber balls are initially at 360 Kelvin because that was the temperature at which they are being cured. And after some time, the surface temperature of the rubber balls are now down to 320 Kelvin. And all the while, the temperature of the surrounding air is at 295 Kelvin. This is a natural convection problem because there are no fluid velocities involved. Now, the first thing that we must ask ourselves is, what is our temperature difference in this case? Since we have two different temperatures for the rubber, that is the initial temperature and the final surface temperature, we have to decide on what temperature we will use on our temperature gradient for natural convection. In this case, we can simply use the bulk temperature or the average temperature between the initial and the final. So we write that our bulk temperature or our average temperature is equal to the initial temperature plus the final surface temperature over 2, that is 360 plus 320 over 2, and the answer is 340 Kelvin. That means that our delta T, or our effective driving force for natural convection, would simply be the bulk temperature 340 Kelvin minus the surrounding air temperature 295 Kelvin. Next, we have to determine at what temperature do we evaluate the properties of the air. Now, do not get confused because even though we were given the physical properties of rubber, those will not be useful for natural convection. What we need are the physical properties of air. And we evaluate the physical properties of air at the film temperature. The film temperature in this case is the average between the bulk temperature and the surrounding air temperature. That is 340 plus 295 Kelvin over 2. That is 317.5 Kelvin. Now we are to evaluate the physical properties of air such as density, viscosity, thermal conductivity, and heat capacity at this value of the film temperature. The density of this air in this case will be assumed to be the density of an ideal gas, and that is Pm over RT. We are assuming that our air is at atmospheric pressure. So our pressure is 101,325 pascals times molecular weight of air 0.029 kilograms per mole. R is 8.314 joules per mole per Kelvin, and then the film temperature is 317.5 Kelvin. Our density is 1.11 kilograms per cubic meters. Now, we also need values for the viscosity, thermal conductivity, and heat capacity of air at this temperature. So you can refer to Perry's Chemical Engineer's Handbook for the values of these parameters. For this example, I have already determined the values of these parameters. So for this example, our viscosity is 1.94 times 10 raised to negative 5 Pascal seconds. The thermal conductivity is 0.0273 watts per meter per Kelvin. And the heat capacity is 1002 joules per kilogram per Kelvin. With those properties, we can now determine the Rayleigh number and the Prandtl number of the system. The Rayleigh and the Prandtl number will be important in determining the Nusselt number, from which we can determine the heat transfer coefficient. Okay, let's start with the Prandtl number. Prandtl number is Cp mu over K. Solving, we have 1002 joules per kilogram per Kelvin. times 1.94 times 10 raised to negative 5 Pascal seconds divided by 0.0273 watts per meter per Kelvin. Our Prandtl number is 0.712. Next, let's estimate the Rayleigh number. The Rayleigh number is simply beta delta T G density squared L cube over mu squared multiplied by the Prandtl number. So this is simply the Grashof number times the Prandtl number. For a spherical system, our characteristic length L will simply be the diameter of the sphere. And based on the problem, the diameter of the spheres are 7.5 centimeters. Let's solve for the Rayleigh number. First, beta, or the compressibility, is simply the reciprocal of the film temperature. That would be 1 over 317.5 times delta T. Our delta T in this case is the bulk temperature minus the air temperature. That is 340 minus 295 Kelvin, multiplied by G, 9.81 meters per second, times density squared, 1.11 squared. You have to remember that the physical properties in the Rayleigh number all pertain to the fluid, not to the solid. Okay? So this is the density of the air squared times the characteristic length or the diameter of the sphere. That would be 0.075 meters raised to 3 divided by mu squared. So that's 1.94 times 10 raised to negative 5 squared multiplied by the Prandtl number 0.712. Our Rayleigh number is 1.37 times 10 raised to 6. Okay, we can now use these values of the Prandtl and the Rayleigh number in our correlation to determine the Nusselt number for a sphere. For the estimation of the Nusselt number for a spherical system, we have here an equation by Campo. That is, Nusselt number is equal to 2 raised to 0.816 plus 0.152 times Rayleigh number raised to 0.277, and that is all raised to 1 over 0.816. We are going to use this correlation because this correlation has been fitted for air and water systems. Okay, let's substitute. We have 2 raised to 0.816 plus 0.152 times our Rayleigh number, 1.37 times 10 raised to 6, and that is raised to 0.277. And everything is raised to 1 over 0.816. Our Nusselt number in this case is 15.53. From this value of the Nusselt number, this is equated to hd over k, wherein d is the diameter of the sphere. We can estimate the value of the heat transfer coefficient by natural convection. So that is Nusselt number multiplied by k, 0.0273, divided by the diameter, 0.075 meters. Our heat transfer coefficient is 5.65 watts per square meter per Kelvin. Now we are going to use our obtained value of the heat transfer coefficient in the second part of our solution, which now covers the unsteady state conduction part. Welcome back, and here are now the data that we can use for our solution in the unsteady state conduction part. So we still have our sphere that was initially at 360 Kelvin. It was exposed to air at 295 Kelvin, and then after a certain amount of time, which we are trying to solve, the surface temperature has gone down to 320 Kelvin. From the previous part of the problem, we have determined that the heat transfer coefficient due to natural convection is 5.65 watts per square meter per Kelvin. And then for rubber, we are given the following properties: the density, the heat capacity, and the thermal conductivity. Okay, for these types of problems, we always start with the determination of the BO number. To refresh your memory, the BO number is equal to H times V over A over K. Now, the K here, or the thermal conductivity, now pertains to the thermal conductivity of the solid, not of the air. Okay, so this K pertains to rubber. Now, for a spherical system, we can solve for our V over A ratio. The volume of a sphere is 4/3 pi r cubed. And for the area, that is 4 pi r squared. Pi cancels. 4 also cancels, so we will be left with 1/3 of R as our V over A ratio. Therefore, our BU number now becomes HR over 3K. Substituting, we have 5.65 times the radius is 7.5 centimeters divided by 2, that is 0.0375 meters over 3 times the thermal conductivity 0.24. Our BU number is 0.29. Now, this is unfortunate because our BO number, which is 0.29, is greater than 0.2, which is our threshold for lumped systems. It is very easy to solve for the time required to change the temperature of a lumped system because it is only governed by one equation. However, since our BO number is greater than 0.2, we now consider this system as a distributed system. For distributed systems, we use the Gurney-Lurie charts as a graphical method of solving this problem in lieu of the analytical method, which uses a Fourier series expansion. For the use of the Gurney-Lurie charts, we have 4 parameters that we have to consider. The first of those parameters is Y, or the unaccomplished temperature change. This is simply the temperature at any point at any time minus the temperature of the surrounding fluid, that is the infinity, over the initial temperature minus the temperature of the surrounding fluid. We can already solve this parameter, and that is our T, or our temperature at any point at any time, is simply the final surface temperature, that is 320 Kelvin, minus the fluid temperature, that is 295, over the initial temperature 360 Kelvin minus air temperature 295. Our Y is 0.38, or we can simplify this to simply become 0.4. Remember that our solution here is graphical in nature, and it will be very hard to read values of Y if you retain many decimal places. Okay? So for this instance, we round that up to 0.4. The next parameter that we have to consider is N. N pertains to your position in the system. We define N for spherical systems as small r over capital R, wherein the small r is your radial position in the sphere, and capital R is the actual radius of the sphere. Okay? Since we are on the surface of the sphere, our radial position is 0.0375 meters. That is the radius of the sphere over the radius of the sphere 0.0375 meters. From this, it is obvious that our N is equal to 1. For spherical systems, if your N is equal to 1, that means that you are positioned at the surface of the sphere. And if your N is equal to 0, that means that you are at the center of the sphere. If you have a value of N that is between 0 and 1, that means you are in between the surface and the center of the sphere. Okay? Next parameter, we have M. M is simply defined as K over H times R for cylindrical systems. You would then see that this parameter is simply the inverse of the BO number. Let's substitute our given to solve for the value of M. K is 0.24, H is 5.65, and then our radius is 0.0375 meters. Our M is equal to 1.1. In the Gurney-Lurie charts later, if you cannot read 1.1 in the graph, then you can round this down to simply 1. Okay? You will see this later in the chart. Now, the final parameter, if we are using the Gurney-Lurie charts, is X, or simply the Fourier number. For spherical systems, X is defined as alpha T over R squared. Alpha is the thermal diffusivity of your system, that is equal to K over rho Cp. Let's first solve for alpha, that is 0.24 over 1120 times Cp 1020. Our thermal diffusivity is 2.1 times 10 raised to negative 7 square meter per second. You can then substitute this value of alpha to our definition of X, but we have to do that later because X contains our variable for time. Remember that we are solving for the time elapsed for the surface temperature to go down from 360 Kelvin to 320 Kelvin. Therefore, X is our missing parameter out of the 4 parameters for the Gurney-Lurie charts. Okay? So our plan here is to utilize the value of Y, M, and N in the Gurney-Lurie chart for spherical systems to determine the value of X. And then once we have the value of X, we can solve for the time. Let's now go to the Gurney-Lurie chart for spherical systems. This is our Bernoulli chart. This is given in Fundamentals of Momentum, Heat, and Mass Transfer by Welty et al. So we are going to use this for this problem. Your y-axis here is your unaccomplished temperature change, for which we already have a value. Our y is 0.4. So looking for y is equal to 0.4. This is 0.1, 0.2, 0.3, and 0.4. Therefore, we will be using this entire horizontal line as our reference value for y. Next, we take a look at our m value. Remember that our m value is 1.1. But if you take a look at this graph, there is no 1.1. It's only m is equal to 1 or m is equal to 2. So you have to choose between these two sets of lines. And of course, 1.1 is closest to 1. So we are going to use the lines for m is equal to 1 as an approximation. If you are given m is equal to 1.5, then you have to imagine that there are lines that are in between 1 and 2 here. Okay? The last parameter we have is n, and our n is equal to 1. So this is our line for n is equal to 1 and m is equal to 1. We simply have to locate the intersection between y is equal to 0.4, which is this horizontal line here, and then n and m is equal to 1, which is this diagonal line here. Okay, so locating the intersection, we see that both of the lines touches at this point in the graph. Okay, if you take a look at my cursor here, it is at this point wherein we need to read the value of x coming from this intersection. So let me scroll down and let's read for the value of x. Okay, the value of x is where my cursor lies right now. So you can see here that this is open for interpretation and that the value is between 0.25 and 0.5. Okay, let's just say that our value of x is 0.3. Going back, if the value of our x is equal to 0.3, we can now solve for the time elapsed. That is simply 0.3 multiplied by r squared, 0.0375 squared, divided by the thermal diffusivity alpha, 2.1 times 10 raised to negative 7. The time it will take to achieve our desired temperature change from 360 Kelvin to 320 Kelvin in the surface is around 2009 seconds. If we convert that to minutes, that would be 33.5 minutes. We have achieved the required of the problem, which is to determine the time elapsed. This is how we use the Bernoulli charts in order to simplify our solution for distributed systems. And also, that is how we utilize the principles of natural convection in order for us to come up with the value of the heat transfer coefficient, which is useful in unsteady state conduction. Thank you for watching, and this has been another problem solved.